All right, so welcome to lecture number 4. To start, I would like to add something to a question that was asked at the end of the last lecture. So I was saying how to stabilize these large extra dimensions that are flat, you typically need to tune. And so I was asked, why is this idea interesting at all if you need to do the same tuning as for just leaving the theory as is? And well, on the one hand, the answer is that, as I was saying last time, this opened a new way to think about the problem, and then work the extra dimension scheme where you could stabilize the radius with asymmetry. But to be completely fair, in that answer, I was referring to the very first paper on the subject. But then people have come up with, actually mostly the original authors of the first paper, come up with ideas to stabilize the extra dimension naturally, even if it's large and flat. Actually, if you ask the questions, they arrive. And one simple way is to add a certain number of branes in the extra dimension with interactions with each other. And this, if you want, it's another way in which there is an analogy between large n and this large flat extra dimension. So you can stabilize this volume that is bigger than you would expect from dimensional analysis using a large discrete number. Or equivalently, you can also have a large conserved charge. So essentially, these extra dimensions would be big for the same reasons that people are big. We're much bigger than a single atom because we have a large baryon number. And these are both ways in which you can stabilize these extra dimensions without tuning. Okay, so this was a small aside because I felt that my answer to the question was not completely satisfactory, and I thank Florian that's following us online for making me honest about this answer, because I mean my previous answer was really referring to the very first paper, and then but it's fair to say that these objects exist also with a natural stabilization. All right, so having said that, we concluded the lecture last time with an argument for why the cosmological constant could be small in a multiverse. So a multiverse can realize many different values of the cosmological constant, but even in that context, we have to ask why we observe such a small and unlikely one, because the way all these values of the cosmological constant are populated is by tuning. So the typical value in a typical universe in the multiverse is still of order m Planck to the fourth, or SUSY breaking scale to the fourth. It's not what we observe. And so we reviewed this argument by Weinberg that was essentially pinning the formation of galaxies to the size of the cosmological constant. Because as we've seen, the cosmological constant determines in the end the size of the region of the universe that you're in causal contact with. And so it has such a dramatic impact on low energy phenomenology that it's easy to find an argument as of why it should be small, provided that you keep the other parameters fixed in the multiverse. But we didn't have time to do the same for the Higgs boson. So again, today we're going to start imagining that a multiverse exists, and we see if it can do something for the Higgs boson. And then after that, I'm gonna tell you how you can actually build a multiverse. So I will give you some toy models of a multiverse. But for now, as I said, let's imagine that a multiverse exists. And then we should ask the same question we're asking for the cosmological constant also for the Higgs boson mass. So if you just pick randomly a universe out of this multiverse, the Higgs boson mass is going to be huge. So why do we see a small one? And well, you can start following the same line of reasoning that led to an argument for the cosmological constant. So essentially, you're asking what changes in nature if you change the Higgs boson mass. And there are many things that change, but the ones that will be useful for us are the neutron-proton mass difference. The neutron-proton mass difference as a piece that comes from the difference in quark masses that compose them, and another piece that comes from an electromagnetic mass difference. So similar to what we've seen for the pions, the protons is charged, the neutron is not, so we're going to have corrections to the proton mass coming from diagrams such as this one. And so long as the up and down quark masses are below the confinement scale of QCD, we can approximately take this fixed. So we can take it to be the value in our universe. And so in this regime, so when the X-Web is not huge, it's not 10 to the 4 times bigger than in our universe, then the proton-neutron mass difference depends linearly on the X-Web. So for me, B is going to take this value for the neutron proton mass difference with the electromagnetic one fixed. It doesn't change too much if you let it change. Another thing that changes with the X-Web is the confinement scale itself. And the reason why it changes is that the scale is essentially determined by the value of the coupling where the theory becomes strongly coupled, and the running of the coupling depends on the mass of the quarks, which in turn depend on the X-Web. And this C parameter here at the exponent is about 0.3, so long as the X-Web remains roughly in this range. This upper bound is roughly when all the quarks becomes heavier than the confinement scale, and this lower bound is when all the quarks become lighter than the confinement scale. Then the dependence kind of saturates because the running becomes more insensitive to the mass thresholds if they are already all below the confinement scale or all above. Well, actually, when they are all above, it's still important, depending on when you start your running, but the power changes. When they're all below, it saturates. And well, as a consequence of these two facts, well, not really the proton-neutron mass difference, but just the fact that the quark masses depend on the web, and the fact that the confinement scale depends on the web, also the pion mass depends on the web. And there is a 1 because the pion mass squared is roughly m up plus m down. And there is a C because it also depends on the pion's web, which, as we've seen in the last lectures, is the same as lambda QCD modulo a coupling of order 4 pi. So there are naturally many more properties of nature that change with the X mass.
Sorry, can you repeat what is the V with which you normalize the wave expectation? What is?
Yes, V us. So it's the one in our universe. Okay. Which is about, well, depending on the normalization you choose, is either 100, well, let's say it's about 174 GeV. Okay. So it means the one in our universe. So this yeah.
No, I understand. I didn't read the us. Okay.
Yes. All right. So okay. So what happens if we take, say, the X-Web much bigger than in our universe? So what happens just as a consequence of these simple facts? Actually, even just the first one would be enough, huh? But the other ones kind of make the argument more precise. So if we take B bigger than the one in our universe, then it becomes much easier for complex nuclei to decay or complex atoms to decay. And so there is a threshold beyond which you have only hydrogen. And it's easy to see it because take any element of your choice, then this can decay to, to itself, where you switch a proton for a neutron, plus an electron and an antineutrino. So what's happening here is really that the neutron is decaying into a proton plus electron and antineutrino. If you want me to write the diagram, it's something like this. So here you have the first atom, here you have the second one. And then a neutron in the first atom turns into a proton by emitting a W minus that then decays to an electron and an antineutrino. And just from the diagram, you can easily estimate what's the rate, so the probability per unit time of this process. It's going to go like the Fermi constant squared times some dimensional full quantity to the fifth that I'm going to tell you in a second. And if you recall, the Fermi constant essentially is just what you get by integrating out the W. So you are imagining that this process takes place at energies much smaller than the W mass, and you are essentially contracting this propagator to a point by ignoring the higher energy degrees of freedom at high momentum. And what's this Q? Well, this Q is just the mass difference between the initial and final state. So this Q is going to be roughly this, where we can safely ignore the electron mass compared to the mass of protons and neutrons. So for those of you that are less familiar with particle physics, the neutron and proton mass is roughly a factor of 1,000 bigger than the electron mass. And this mass difference, well, these two elements are the same, except that on one side you have a neutron and on the other one you have a proton. But then you also pay a price in binding energy in the decay. And this number Bn is always positive, because when you switch a neutron for a proton, you have some extra repulsion in the nucleus due to the electromagnetic force that wants to break the protons away from each other. And so you see already by this very simple parametric form for the decay rate per unit time of nuclei, and the fact that it goes like proton-neutron mass difference to the fifth, that if you take B bigger and bigger, this rate rapidly grows. And at some point, the lifetimes of all atomic elements become tiny. They all decay, you're left with only hydrogen. And the bound that you can get on B from these, if you want elements that are stable long enough, say, to support life, is pretty striking. So you have to keep the Higgs vacuum expectation value roughly 5 times within a factor of 5 of the one in our universe. So that's a pretty strong bound. And well, if for you asking for the existence of complex chemistry is something important to have observers, this is telling you why universes that have a negative Higgs mass squared, which is much bigger in absolute value than the one that we observe in our universe, are not compatible with the existence of observers. For now, let me leave it at that. To be honest, I mean, I'm not a huge fan of this kind of arguments, because you can already see that they're becoming much more detailed than for the cosmological constant. So here, you're kind of implicitly specifying the kind of observers that you're interested in. It's not as robust as for the cosmological constant, where essentially we're just asking for enough entropy inside an horizon. Here you're really asking that observers come from some specific complex chemistry. For example, one loophole in this argument that I don't think has been explored in great detail is what happens if you make the Higgs-Bev really huge. When you make the Higgs-Bev really huge, what happens is that the baryons, like this guy, which are made of up quarks, become the lightest ones. So at some point, this will be your lightest baryon. All the protons decay, all the neutrons decay, you're left with a universe with these baryons and electrons, let's say. Okay, but then I'm not sure that anyone has checked whether you can have molecules and atoms made out of these baryons and electrons, which is not completely impossible, because in this universe is also the hierarchy between electromagnetism and nuclear force is changing as a consequence of the fact that the pion mass is changing. So you see, the reason why I wrote down this equality here to make more precise that argument is that you might have worried that the binding energy was doing something weird with the X mass. But the leading description of nuclear forces, what keeps the nuclei bound together, comes from pion exchange. And you see that as you make the X web bigger, the pion mass is also becoming bigger. And so the force induced by pion exchange is becoming weaker. In the same way as if you increase the W mass here, the weak force is becoming weaker because it's controlled by this effective coupling, which decreases with the mass. And so as you make the X web bigger, in this argument, you don't only have the effect that the neutron-proton mass difference becomes bigger, but also the fact that the binding energy becomes more negligible. And so these universes are not trivial at all. So it's not so easy by just staring at the blackboard to say that there are no molecules, no chemistry. They are very different from our own. And I'm not aware of someone having worked out in detail what happens. This, I think, if I remember correctly, happens roughly when the web becomes 10 to the 3 times bigger than our own. Anyway, so setting this aside, let's even say that we're not worried about this, okay? That we have done the calculation and the universes where only their delta plus pluses and electrons are sterile. You can do nothing but at most some atom with a delta plus plus and 2 electrons, and that's it. But we still haven't explained what happens when the X mass is positive and big. And in this case, there is not an argument that is quite as sharp as that one. There are a bunch of more end-wavy reasons for why observers might not arise in these universes. So for one thing, in these universes, the W and Z masses are much smaller. Okay, so in these universes, the X starts its life with 0 vacuum expectation value, and then it gets a small vacuum expectation value from the condensation of QCD. So QCD still becomes strongly coupled in these universes if you keep the other parameters fixed, but at a much lower scale than in our own. So it becomes strongly coupled at a scale of about 30 MeV. And then the X gets a web from the fact that you can write its potential like in the standard model, with the leading interaction with the fermions coming from the top quark. And then below this scale, the bilinear of 2 top quarks develops a vacuum expectation value roughly for the scale where QCD becomes strong. And then if you look at this potential roughly at this scale, the mass term dominates over the quartic. So roughly you have a potential that looks like mass plus tadpole. And if you look for a minimum, you'll find that it's roughly at this value of the field. And so all the fermions in this universe are very light. So they are all below this confinement scale because their mass, so if the theory was still perturbative, you would say that their mass is this, which is roughly equal to what we just derived. So up here we have something of order 30 MeV cube. Down here we have something much bigger than 100 GeV squared. If you put the numbers, it's easy to convince yourselves, given what are these Yukawa couplings in the standard model that go from Y top being of order 1 all the way to Y electron being of order 10 to the minus 5. So it's easy to convince yourself that all the fermions are below this scale. And so for the quarks, it doesn't make too much sense to talk about their masses because they're confined. But you can think of these masses in the same way as we think of these masses for the up and down quarks in QCD. So they tell you what the pion masses in these universes are going to look like. So why did I tell you that that the fermions are so light? Well, mainly for the reason that if you want, again, complex chemistry, you have to wait until the universe has cooled down at least to an energy that's smaller than the typical energy that you need to break down a molecule. Because if the photons in the universe are energetic enough to break all the molecules, then you live in a universe without any molecules, obviously. And the energy, the typical energy of a molecule is something of order this, which I'm going to tell you why it looks like this in a second. And this epsilon is a number of order 10 to the minus 2, 10 to the minus 3. So you see that the typical energy that you need to break down a molecule in this kind of universe is orders of magnitude smaller than in our universe, because now for the mass of the electron, you have to plug in this value here. While in our universe, this number here is replaced by something of order 100 GeV. And so it might just be that by the time you need to wait until the universe has cooled down enough not to break down any molecules, maybe the cosmological constant already dominates. So as you can see, it's not a very precise argument, but it's one possibility. The other thing that you could argue as of why observers don't exist in this universe is that, as I was saying, also the W and Z masses are much smaller, because in the standard model, they're dominated by the Higgs vacuum expectation value. However, we've just seen that in this universe, it's quite small. In particular, it's smaller than the scale where QCD confines. And so the dominant electroweak symmetry breaking scale in this universe is really the QCD condensate itself. So you can write down a chiral Lagrangian that describes the pions in this universe with Z and W bosons still in the spectrum. So you get all the way down to the scale, and the W's and Z's are still masses. SU2 left is unbroken. And then below the scale, you write down a Lagrangian of pions that looks like this, where these U's are fields containing the pions, and these covariant derivatives contain the SU2 left gauge bosons. And then if you write also the potential for these pions, you will find that they get a web of order lambda QCD. And this web of order lambda QCD gives a mass to the W and Z bosons in the same way as the Higgs web gives it to them in the standard model. But the whole point of this very quick overview of these universes is that now the W and Z have masses of order this times a weak coupling. And so if you look at processes that violate baryon and lepton numbers, which exist in the electroweak sector, these processes turn off at a much lower scale. And so if imagine that you generate a matter-antimatter asymmetry at 100 GeV. Then what would happen in these universes is that these electroweak processes that violate baryon and lepton number would wash out all the baryon asymmetry. They would move it into the neutrinos. And so in our universe, we have observers because there is a matter-antimatter asymmetry. We are entirely made of matter. But imagine now that the number of protons and antiprotons was exactly the same, and the only asymmetry was in neutrinos. Then again, you could not make observables. I realized that for people that have not thought too much about this and don't have the particle physics numbers in their head, this is very quick and might be confusing. But as I said multiple times, the goal of these lectures is to expose you to as many ideas as possible. So I'm trying to do it in the smallest possible number of steps that still makes logical sense. But if it was confusing, please ask. I'm happy to answer. And you will also find slightly more detailed descriptions in the notes. Yes?
I missed the argument. Can you repeat, please, why in that case the baryon asymmetry would be erased?
It's just that, I mean, okay, again, you have to make some assumptions. So if, let's say you assume that you generate the baryon asymmetry much above the scale, then sphalerons are active down to the scale roughly. And so they move everything into neutrinos by the time they freeze out.
Is it because the electronic phase transition will occur after the QCD phase transition in that case?
It would occur, yes, roughly almost at the same time, but a little bit later because of the weak coupling. I don't know if it was completely clear, but yes.
Yeah, I was gonna ask if you had the similar cosmological arguments for the first part where mh square is negative, but if you have a small VEV and you get the electroweak phase transition very at low temperatures, is something gonna go wrong? Or?
Yeah, so if you make it too small, so you want mh square negative but a small VEV, or yes, is that the question? Yeah, I mean, yes, indeed. I mean, if you make the phase transition happen too late, then this might happen. But as you can see, I mean, so the bottom line of all these two stories for the mh square positive universes is that there are some arguments, but they all depend on other assumptions. Like here, you're assuming that the asymmetry in baryons is generated above this QCD phase transition. Similarly, in the case of these other universes, indeed, I mean, if you lower B a lot, but you keep it non-zero, then you have a similar problem. However, I'm less worried about small b than zero b, because universes with small b are more tuned than ours. So you might just say, okay, these are more unlikely in the multiverse, I don't want to worry about it. Instead, these universes here, they look like this, even if mh squared is m Planck squared. So they're much more likely than our own. So you have to worry about them much more. But anyway, so what I was trying to say before the questions is that, yeah, these arguments exist, but to me, they're not fully convincing. Even the most robust one, the one about chemistry, requires some assumptions on what you call an observer. So I would say that most people regard the existence of a multiverse and these anthropic arguments as a caveat. So you should keep in mind that if a multiverse exists, maybe an explanation for the XBEV is not going to appear in a manifest way out of symmetry in your own universe. But no one really believes to the decimal point this kind of unwieldy arguments. Besides, something to keep in mind is that even if you have a multiverse, a symmetry explanation remains more likely, because to get without any symmetry, if you want to get the x bar small or the cosmological constant small, you have to tune. Okay. Now imagine that you have a symmetry and a multiverse. Now the symmetry breaking scale can change from universe to universe, but the probability distribution for where the SUSY breaking scale should be in the multiverse is essentially uniform. So it doesn't depend on tuning or anything else. It just depends on where you're breaking the symmetry. Of course, to know the exact distribution, you have to make some assumptions on the UV, on what's generating really this multiverse and this supersymmetry breaking scale. But what I'm trying to say is that there is no price to pay to make a symmetry breaking scale small. Instead, there is a price to pay to make a dimensionful parameter small without any symmetry. So if you have a multiverse where supersymmetry can be realized, it seems naively much more likely that you see a small XBEV or a small cosmological constant, because the symmetry breaking scale is small, rather than you're just canceling randomly different contributions to the XBEV or to the cosmological constant. Okay, but having done this little digression, let me give you a maybe less popular, but I think more interesting way of explaining a small Higgs mass in the multiverse. And then after that, I'm gonna tell you how to make a multiverse. So I will give you a few toy models of how to populate many different values of the cosmological constant and or of the Higgs boson mass squared. And in doing so, I will also explain what's the, I would say, most popular explanation for the cosmological constant. So Busso-Polchinski's idea in the 2000s. Okay, so a way I like to explain the Higgs mass in the multiverse is essentially to write a model where I can use the same argument as for the cosmological constant. Let me write a simple toy model. This is, I think, the best toy model for pedagogical reasons. It's not, of course, the best model ever, but it's the one where you have the best possible description of how it works in 5 minutes. So let me imagine that I've added to the standard model 2 scalars that I'm going to call phi plus and phi minus. These 2 scalars have a potential, but this potential is small in some sense, meaning that they have an approximate shift symmetry. The potential breaks it, but not by a lot, at least compared to other particle physics scales. And I want to imagine that these 2 scalars have each their own potential. And this is just a simple phi to the 4 plus phi to the phi square plus phi to the 4 potential. Okay, just written it in a slightly different way, but you could call this lambda. This would be the usual Higgs-like potential. The reason why I'm calling this a toy model is because I've chosen this negative sign for the quartic. So really this potential has a runaway direction that I have to imagine to UV complete somehow. But allow me to just consider the toy model, which is certainly valid for field values that are smaller than this m. So the reason why I've written the quartic in this way is because it makes immediately manifest that the typical web of the scalars is m, at least wherever this description is valid. And
so m square is positive. M
which
square,
square?
plus.
The mass?
Yes.
Yes. It's that's what I was about to say. Indeed, so I want to take the mass positive. In which case, if you just draw the potential for phi minus, you're going to get something like this. So this region around the origin is of size m minus, so the distance between the 2 maxima. And then it has the runaway direction, okay? I'm imagining that this is UV completed into something that gives it a stable minimum very far away compared to my m minus, but for our exposition, it will not matter too much. And phi plus looks similar, only it doesn't have a minimum near the origin, it has a maximum. And the region over which the potential is relatively flat, so where the mass term is still dominating, is of order m plus. Okay, so when you go farther from the origin than m plus, the negative quartic starts to dominate and you start to run away. And also in this case, I'm imagining that this is really completed to something reasonable. So this is the situation without the standard model, but then I'm adding also a coupling to the standard model. So these are two gluon field strengths. I'm summing over the gauge index A. I'm also constructing the Lorentz indices, and this tilde here just means that this is the antisymmetric contraction of the full field strength. So this is CP odd, and this is an axion-like coupling. So you might be already suspicious because I'm taking some field that looks like a phase, so it has a axion-like coupling, and I'm giving it a compact, non-compact potential. But as the assumptions that I'm going to make, which are consistent with the symmetries of the model, because these two pieces of the potential are breaking the shift symmetry differently, are that the scales f are much bigger than the scales f. Okay, this is completely technically natural. Is essentially the same way as saying that in QCD, roughly the same thing of saying that in QCD f pi is much bigger than the quark mass. It's not exactly the same, but in spirit is the same because these two scales are breaking different symmetries. And so why did I give it this coupling? So I gave it this coupling because
sorry, what's the term in the sum?
This theta. So
okay, theta.
This is
okay.
a constant.
No, okay. I didn't read it.
So this theta is there.
Okay.
Just in the standard model Lagrange.
Okay.
And actually, it's interesting because it's another parameter that we don't know how to explain. So naturally, you expect it to be order 1, but we measure it to be 10 to the minus 10. And the cute thing about this idea is that it tells you simultaneously why the x bus is small and why this parameter is also small. Okay, so now this is the full theory. Okay, axion-like coupling plus phi squared phi to the fourth. So what happens to this theory if I run it to the history of the universe? So initially, let's say that the universe starts its life at some temperature much bigger than the QCD scale. Then up here, I only see this potential. And I can write the equation of motion for these scalars, which is exactly what you get from the action. And it's going to look like this. And so, as long as this term dominates over the derivative of the potential, the scalars are stuck. Okay, so if this is not an assumption, it's just something you can just solve the equation and see that if this is true, then the scalars stay wherever they started their life. And this is important because let's say that they didn't. If they didn't, then this phi plus would roll down. The cosmological constant of the universe, as you roll down, it's going to increase, become larger and larger in absolute value, but negative. And so at some point, it will dominate the energy density of the universe and make the universe crunch, as we said last time. So whenever you are far enough from the origin of phi plus or phi minus, you're in a situation where the universe is contracting exponentially with some phi dependent cosmological constants, as we've seen last time. But this happens only when the scalars start to move, okay? At some point, they will start to move because as the universe expands, Hubble decreases. But let me imagine that the mass of these two scalars, or at least the one of phi plus, is smaller than Hubble at the time of the QCD phase transition. If this is true, then all universes have a chance to survive all the way down from this temperature to the temperature of the QCD phase transition. The reason why I care about this particular temperature is that at this moment, this coupling here will generate another contribution to the potential of these two scalars, and it will change the equation of motion. Unfortunately, we don't have time during these lectures to derive the fact that from this coupling you get a potential, so you will have to believe me. But believe me, what you get down here is this. And this expression is true in the limit that I said I would consider. So when f is much bigger than m. So now we're looking at the potential, again, in a region of order m plus and minus around the origin. And this lambda QC to the fourth, that I explicitly written that it's a function of the xvev, looks like this. And again, you'll have to believe me that this is a monotonic function of the xvev. If the xvev grows, lambda QCD grows, and this potential grows. If the xvev decreases, so does this potential. Okay, this is important. And so what happens now? So at this point, the scalars start to move. So if this potential is negligible compared to the initial potential, we will die. So all universe will eventually get a big negative cosmological constant and crunch. But let's say that this potential is not negligible compared to the one for the scalars in isolation. Then it can have some effect on the dynamics, and it can determine which universes survive and which universes crunch. And you see already where I'm getting at, because this potential depends monotonically on the xvev, and it also depends on this theta parameter. And so we're going to have a range of values for the xvev and for this theta parameter for which the universe survives, and a range for which the universe crunches. Let's see it immediately. So let's imagine for simplicity that m phi minus is bigger than m phi plus, okay? This is another one of these assumptions I'm making that is not really necessary for the idea to work, but it just makes explaining it much easier. So if this is the case, then phi minus starts to move first, when phi plus is still stuck. And let me further imagine that f minus, again, is much, much bigger than m minus, so that the coupling to the x of phi minus gives me a potential that is roughly just the linear part. This is some theta effective because it's given by whatever theta was plus wherever phi is initially. Okay, so roughly it's going to be of the order of this. The reason why it's going to be of the order of this is that if phi plus starts its life very far from the origin, you're already dead. So you don't even need to think about these universes. And so what happens here? So what we did is that we added to the original potential of phi minus a term that looks like a tadpole, so something that looks like this. And so their sum, it's going to look like this. And you see that if you keep increasing the size of this tadpole compared to the original phi potential, eventually you will destroy this minimum. So as you increase it, this thing will look more and more like this, and eventually it will just look like this. And the value of this tadpole depends on the xvev. So as you make the xvev bigger, you're going towards this direction. And so the requirement that phi minus doesn't crunch the universe, so doesn't kill you, is setting an upper bound on the xvev. So phi minus is telling you that the xvev should be smaller than some critical value that is determined by the size, essentially, of the phi minus mass squared. So this is setting an upper bound on the xvev. Essentially, it's telling you why we do not exist in universes where the x mass squared is negative and big. And that's why I called it phi minus, because it kills all the universes where the x mass squared is negative and big. And so you see now what phi plus does. Phi plus does exactly the opposite. So after this has already taken place, let's say that we are in a universe that is safe. So we started our life with both phi minus and phi plus close to the origin, and the X tadpole is not big enough to kill us. So now phi minus has done whatever it had to do. So phi minus is somewhere here and it's oscillating around its minimum. And now we look at the dynamics of phi plus that starts moving second. Well, now the potential of phi plus looks like what it was before, plus what we get from the standard model coupling. And now let me take again, phi plus is much bigger than m plus, but not so big that I don't see the quadratic part. Where again, here you have some theta plus effective, and your theta plus effective is whatever theta was plus the position of phi minus at the relevant time. And so you see again that this potential is instead now killing all the universes with a large positive sigma square, and where theta is too big. The reason is the following. So if you just keep phi plus in isolation, eventually you will roll down and die. So you need this second piece of the potential that instead looks like this to sum with this one and give you a local minimum. So you have phi in isolation plus phi plus x, and you want the result to be something like this, so that you have a safe minimum near the origin where you are alive. And for this to happen, you need two facts. The first one is that the size of this mass term, sorry, here there is an f, not an f. The size of this mass term should be bigger than the negative mass that phi plus n initially. But that's not enough. You also need the mass term, the positive mass term, to turn on near the origin. And this was setting a bound on theta, because this term essentially can shift where this potential becomes important. And if it becomes important, let's say here, where the quartic term for phi plus is already dominating, you have no way of generating a minimum. Okay? Here I'm saying in words something that you can convince yourself with very simple algebra. So if you just sum these two potentials and look for a minimum near the origin, you'll see that you are going to have one only if your theta effective is smaller than some critical value, and your lambda QC to the fourth is bigger than some critical value, or equivalently, if your xVev is bigger than some critical value. So altogether, you set a range where the xVev should be, which depends on the masses of phi plus and phi minus, and you've also set an upper bound on theta. Yes.
How complicated is it to survive? And because you need to, say, from reheating to QCD without moving, right? If I understand correctly, from your new potential.
Well, so you just need to be, so, okay. Notice that these guys are very weakly coupled to the standard model. So essentially what you're assuming here is that their sector is not reheated very much, okay? If that's the case, then to survive, well, you need, of course, these three conditions to be true, which is what you want. But you also need to be a bit lucky. So you need to start your life close to the origin, so in a region of order n plus minus near the origin. So in this model, let me tell you honestly what's nice and what's not nice. What's nice is that you are turning, so you're giving a very robust reason why the xVev should be in a certain range and why theta should be small. Essentially, it's the same argument as for the cosmological constant. If they're not in a certain range, the universe crunches. So I mean, it's easier to imagine that you don't have observers in such a universe with a tiny radius of curvature. Another thing which is nice, which I'm going to emphasize more, I think, in the last lecture, is that it's leveraging a connection between strong interactions, and in particular the theta parameter and the X-web, which is completely ignored in symmetry-based solutions to the problem. So this idea is leveraging the fact that the only local operator in the standard model that this vacuum expectation value depends on the X-web. So the only local object in the standard model that cares about the X-web or the X-mass is this. Okay, and we're going to talk more about this in the last lecture, which is, so essentially, even if you don't like the model, it's telling you an important fact about nature, that the standard model itself is telling you that in some precise sense, the X-web and the theta parameter have a connection. So these are, let's say, the two reasons why I like the model. The two reasons why I don't like the model, well, let's say the reason why I don't like the model is that it's making implicitly a big assumption on the UV. So in this story, we are implicitly imagining that there is a multiverse which is scanning, so it's populating different values of the X mass, of the theta parameter, and the cosmological constant. And so in the UV completion of this model, you are effectively saying that whenever you are at the minimum of one of these two scalar potentials, no other thing in the multiverse is able to raise the CC. Okay, so this minima of these two scalars, which is also the one that couple to the X, have to be very deep, because you have many other contributions of the CC in the multiverse that all cancel each other. And here, they can easily cancel the CC coming from phi plus and phi minus. But in your UV complete model with the deep minimum, in this minimum, they shouldn't be able to cancel the contributions to the CC of phi plus and phi minus. So you are putting some strain on the UV. So the UV of this theory is not trivial. However, the low energy set is very simple. And also, it's not so hard to UV complete this model. Maybe I will comment more about this when we get to the relaxation, since I'm already nearing the end of the first hour. But as I was saying at the beginning, you might feel awkward that you have a compact part of the potential and a non-compact part. But as you can see, the period of the compact part is much bigger than the typical size of the non-compact part. So this is not so bad. Essentially, it's saying that you haven't seen that this phi lives on a circle because you've looked only at a small interval of the circle, and then there it can look flat. Okay. What's a bit more laborious is to UV complete the whole thing, because when you add the deep minimum far away, you want this whole potential to live in a small segment of the circle. For the relaxation, instead, is the opposite. So they want this F to be much smaller than a typical scale of the non-compact potential, and then it's almost impossible to UV complete. But this is for the next hour. I think I've gone way too slowly, but well, I think that this gives you a very incomplete overview of what you can do in a multiverse. The bottom line, really the message to take from these models is that if you start thinking about a multiverse, you also start thinking about the problem in a completely different way. So you see that the predictions of this kind of ideas, now I showed you only one, but next time we're going to try to give a broad overview of the predictions of this kind of ideas, is that you have two scalars that are coupled like axions to strong interactions. And I didn't show you the numbers, but if you run the numbers for what you need for the weak scale to be the weak scale, you'll find that their mass is very small. So it's kind of axion-like. In this model in particular, you can make even a more fun prediction that the neutral electric dipole moment is related to the mass of dark matter if these guys are dark matter. But setting that aside, which is more model dependent, the more model independent part of the story is that you accepted the existence of a multiverse, then you built a model to explain the X mass, and you find completely different consequences compared to what you were finding in terms of symmetry. So we might spend our whole lifetimes arguing whether these theories are better or worse than symmetry-based explanations. We all have our opinions and inclinations, but it doesn't matter. The final answer will come to experiment. So the predictions of these guys have nothing to do with the predictions of models with asymmetry explained in the weak scale. And that's enough to me to make them extremely interesting, because for decades, we have tried to guess what's the theory of nature. Sometimes we were right, and sometimes we were completely wrong. And the only way in which every time we go back to the right track is that experiment kind of pushes us back towards realism. And so at the moment, we don't know yet the answer. So it's important to come up with qualitatively different ideas that you can test and compare. And this is a very striking example of how two explanations of the same problem can be completely different. So if you remember, when we were explaining the X-web in terms of symmetry, we were predicting a whole tower of new particles with interactions similar to those that already exist in the standard model, with coupling to our gauge groups, things that in principle we could produce at colliders, so that could give signals into rare decays of standard model particles. And here we're saying something completely different. We're saying maybe the problem is explained by two very light, very weakly coupled scalars that you're going to see when you look for axions in alloscopes or holoscopes or whatever is your favorite axion experiment. And so this is, I think, a good place to take a break. It's about an hour since we started, and then in the next hour, the first thing I want to do is to build some multiverses, so show how you can change the values, for example, of the cosmological constant from universe to universe, and also of the Higgs mass. And we're going to do it using non-dynamical four-formed fields, which seems a lot of unnecessary work, but we do it because these fields actually exist in string theory, and they're built into the most convincing explanation that we now have for the cosmological constant. So the next hour, given how slowly I've gone this first hour, is realistically going to be devoted mostly to the cosmological constant.
Questions?
Stefan?
Maybe a very late question. In the end, what does the multiverse picture add to simple anthropic arguments?
Yeah, that's a good question. So, so the value of theta also matters for a lot of nuclear properties. So, for example, say the neutron-proton mass difference grows like, I think it grows, but anyway, scales like theta squared. The binding energies of many of the light nuclei that we see in BBM, for example, like deuterium, I think also scales like theta squared. So if we found that if theta was order 1, you could change quite a bit nuclear interactions, let's say. But between 10 to the minus 10 and 10 to the minus 3, there is almost no difference. So I'm not aware of an argument that can get to 10 to the minus 10. So what's the difference between this 10 being 10 to the minus 10 or a much bigger but still tiny number compared to order 1? I have no idea. So this is my answer. Not fully satisfactory, but I think that the bottom line is that there is no good anthropic argument because of this. Well, okay, there are other properties still. Also, the pion mass depends on theta at order 1. But again, if theta is 10 to the minus 10 or 10 to the minus 5, we don't even have the experimental precision to tell from the pion mass. In some sense, the fact that the best determination of theta is the neutron ADM is already telling you that we don't have a good anthropic argument, because if you make the neutron ADM 1, I think life still exists roughly in the same way. And so, yeah, that's the answer I know at the moment.
Yeah, so in this model, so you explain that you get an upper bound on theta,
yes,
and the finite range for the X, but I didn't see how this upper bound goes to 10 minus 10, and how you get the interval for the x, which is the one you want, which is experiment in numbers.
Yes. So let's, for example, look at the upper bound. So for the upper bound, you want this tadpole not to destroy the minimum that already existed. And so roughly, you're going to have a condition on how big lambda QCD should be compared to the potential that I deleted. Sorry. So let me write it down again. So essentially, you want a so to get the upper bound, you're asking that this tadpole is such that the minimum occurs before the quartic dominates, because otherwise you have no minimum. And so essentially, you're gonna do this. So you solve for the minimum of phi minus without the quartic, so just mass and tadpole. And this is gonna give you lambda QCD to the fourth. It's a function of the step. Let's see. So times f. No, sorry, divided by f minus divided by m I minus squared. So if I didn't make any mistake, because you're gonna do phi, yeah, I mean this seems right. Maybe there is a minus sign, but it doesn't really matter. Okay, let's use the minus sign. And so you want this to be smaller than m minus. And so this is telling you that lambda QCD to the fourth is smaller than phi minus squared and minus f minus. Okay.
Well,
so,
without the minus, maybe. No, in the absolute value.
Yeah. Sorry. Yes, sure. Exactly. Yeah. That's good. Yes. And then you can do the same for the other upper bound and for theta. I mean, if you want, I can do it, but it's roughly the same steps. And so essentially, this is telling you that the maximum value that you see for the weak scale in this model depends on what's the mass of the scalar and what is the K constant, let's say. So it's effectively, when you measure the weak scale in our universe, you're measuring the mass of the scalar. So it's telling you what's the typical mass of the scalar in this universe. In the end, you have more free parameters than measurements. So you have some range in which this works. So for example, the scale M is essentially free. The only condition that you have on M is this, that should be smaller than the observed theta. So you have a condition on the ratio of M over F, but you don't have a condition on their absolute value. So essentially you have one, so you're left with 1 degree of freedom once you put in all the bounds, which is the typical scale. And so you can play with it, making it heavier or lighter. But then at some point, some experimental bounds kick in, because you cannot have scalars like these arbitrarily strongly coupled to us. And so in practice, you find that this works in the usual range in which the QCD action is alive. So if you plot where these particles live in a plane of mass times 1 over decay constant, you're going to find roughly the usual exclusions that tell you that it should be lighter than about 1 electron volt. And then, okay, there are also some holes at bigger couplings, but since the mass comes, it's comparable to the one that comes from the QCD phase transition. Typically, you don't go with decay constants that are smaller than the QCD scale. This was a bit quick, but I can give you the paper for more details. I also don't want to like suck up the whole break. Yes.
When you call the term Higgs 5 plus 5 minus a tadpole, you mean a tadpole where there is a gluon field, something like that, and the external legs?
But no, by a tadpole, I only meant that it's linear in the field. That's all I meant. That I mean, yes, that I'm taking the hierarchy between F and M for F for phi minus, such that the only term that's important of this potential, well, so this is an expansion. This is an expansion in phi over F. And the actual potential that comes out of here is something that looks like 1 minus sine squared of phi over F plus theta, with some numerical, with some factors in front. So that's the full potential that you have if you do the exercise of seeing what the coupling to the gluons gives you at low energy. And but I'm taking this hierarchy of scales, and then I'm expanding this potential so that the leading term will be this quadratic term. And I'm further imagining that for the case of phi minus, the scale is so much bigger than M that all that matters when you minimize your potential near the origin is the linear term that comes from that potential. And so then I'm focusing on this guy.
In lambda QCD to force, where does it come from? There is some
the dimension full scale in front.
Yes.
So when you normally, so when I do the 20-hour course, I do first the derivation of this potential, but here I didn't have time.
I mean, you have a QCD loop or something like that?
What happens? Well, yes, in some sense, yes, but it's not so easy in the sense, I mean, it's not one loop, it's infinitely many loops,
Okay.
because you are, I mean, the way in which you actually compute this potential is, so at high scales, QCD is approximately perturbative. So you write your Lagrangian that includes this term, and that includes also the other interactions of QCD. In particular, you're going to have a term that looks like this. So the quark masses. Okay. You can do a change of variables in the path integral. So and well, if you see how the path integral measure for the fermions transforms, it transforms in such a way, well, let me call it alpha q, okay? It transforms in such a way that, never mind, that these, so I might be wrong on the order one numbers, but if you choose the right order one number in the phase, it cancels this, and then, but then you end up with something that is phi dependent in the quark mass matrix. Okay, and now you arrive at lambda QCD. At lambda QCD, the theory becomes strongly coupled, and these are not anymore the good degrees of freedom to describe the theory. But since QCD has an approximate SU3 left cross SU3 right symmetry at this scale, where these SU3s act on the quarks. So at this scale, there are 3 quarks, up, down, and strange. And if you ignore the masses that are much smaller than this scale, at least for up and down, then there is this approximate symmetry of the Lagrangian, which is explicitly broken by the masses. And so you can write an effective Lagrangian of Goldstone bosons of this symmetry, and you can match the UV Lagrangian to the higher Lagrangian of the Goldstone bosons. In particular, the symmetries allow you to match the mass terms easily. And so if I call M the mass matrix of the quarks with all the phi's inside. Okay, there are the phi's, the diagonal elements. Then, in the low energy theory, let's say the term that gives a non-zero potential to the Goldstone bosons looks like this, where this U is my usual nonlinear representations of the pions. So these T's are the generators of SU3 of the SU3 that remains unbroken after QCD becomes strongly coupled. Because when QCD becomes strongly coupled, this is spontaneously broken to the diagonal subgroup. And actually, sorry, these are the broken ones. And now, okay, now in this theory, essentially you expand your Goldstone bosons, you expand your quark mass matrix in terms of phi, and then you can first minimize the potential of the Goldstone bosons, see that some of them have a VEV, expand the potential around their VEV, then integrate out the Goldstone bosons because their typical mass is of order what I was saying before. So it's the typical mass is m up plus m down times f phi, while the typical mass of phi is let's say so this is so the typical mass of phi is the same thing that it's in front of the potential of everyone, but divided by the bigger decay constant. So phi is the lightest one in the theory. So you can integrate them out, which are heavier. I mean, the only point is that here you have for everyone something like this. Okay. So when you expand the two, you see immediately that these guys have a mass that's given by roughly f pi lambda QCD squared times the quark masses. And instead, this guy m has the same but suppressed by bigger f. So you can go to another simpler effective theory where you integrate it out the pions, and in the simpler effective theory you get this. So I realized that again it was a bit quick. Typically I do it in 40 minutes in a lecture, but that's the step-by-step way in which you get this potential.
Okay, but more or less I see.
More or less. Yeah. I mean, then there would be, I mean, if you want, there is also a UV step where you show that this is, I mean, how this is a natural capping for a Goldstone boson, so Wi-Fi is also compact. Okay, here you see it after you rotate it in the quark mass matrix, but there is also a UV way to see it. Yeah, yes. I mean, I do wanna say a few things. So during the break, when all people following online were not able to listen, I got a very interesting question from Patrick in the audience about the significance of the fact that these anthropic arguments squeeze the cosmological constant and the X-VEV into very precise ranges. Because let's say that you explain them by asymmetry, then how come that they are so small? Sorry, they're in such narrow ranges. Okay, so if you explain them in terms of asymmetry, then by measuring them, you're just measuring some symmetry breaking scale. So it's not a problem that their values are fine-tuned to some experimental number. That's not a problem. It's just a statement that by measuring them, you're measuring some other parameter in your theory, which could be the symmetry breaking scale. But then you're still left to wonder, why are the parameters in our universe so fine-tuned so that observers can exist? And the funny thing, which I forgot to mention before, is that if you look for these coincidences, you will find many more. And one famous example is that when a star runs out of hydrogen, then it collapses, and then at some point, its core temperature arrives at 10 keV. And when this happens, then a new set of reactions starts taking place. So in two helium atoms can fuse into a beryllium. And then another helium and the beryllium can make carbon plus 2 photons. And then another helium and carbon can make oxygen and a photon. And well, the funny thing is that if you want enough carbon to sustain life as we know it, you need the excited state of carbon in this reaction to lie between 7.3 and 7.9 MeV. If you want to observe the amount of carbon that we observe in nature, you need the state to be between 7.596 MeV and 7.716 MeV. And oil used this fact to predict the existence of this excited state of carbon. And this is not the only fine-tuning just purely within this reaction. The other fine-tuning is that if this excited state of oxygen was again displaced by some small fraction of an MeV, this reaction might be too fast. So you might deplete too much carbon and again not have enough for life. And so this is one of many examples of coincidences that happen in nature and that sustain life as we know it. There is actually an entire book devoted to these coincidences, which is called the Cosmological Anthropic Principle, which contains a lot of fun physics. Essentially, it reveals the whole universe, starting from atoms and molecules all the way to stars and beyond, from simple dimensional analysis relations, and shows you that there are a lot of striking coincidences like this one. Another one that is very important for stars to exist is this one, which is a fact of nature that by eye might mean nothing to you, but it determines the existence of stars like the sun that radiate energy outside of their core. And as I said, if you start looking for these coincidences, you will find enough to fill up a book of hundreds of pages. And so, well, I mean, you can take this in many different ways. The authors of the book use this to try to prove the existence of God. If you're thinking about the existence of a multiverse, then you might be more of a relativistic thinker and realize that these are big coincidences only if you imagine that you're changing just one parameter in your equations. And the same is true for the Higgs mass and the cosmological constant. If you start imagining that all parameters in your Standard-Model-Lagrangian change from universe to universe, then there are no more striking coincidences. For example, the argument I gave before for the Higgs web was essentially entirely relying on the difference in mass between the down and up quark, at least when it was coming to setting an upper bound on the Higgs web. And so you see immediately that it's true that this scales like the Higgs web, but it also scales like the difference in down and up Yukawa couplings. And so here you have immediately a flat direction. If at the same time as you're changing the Higgs web, you're changing also the up and down Yukawa couplings, this mass difference might remain fixed. And that's, in some sense, the biggest assumptions of all these ideas relying on the multiverse is that in the end, they're asking for many of the parameters of the standard model to remain fixed while the dimensional parameters change from universe to universe. There is actually an instructive toy model of the multiverse by Nimar Kamialev, Samas Dimopoulos, and Shamit Kakshu, whose name I hopefully pronounced correctly. I'm not sure. I apologize if I didn't. Where they show how to build a toy model of a landscape or a multiverse that scans only dimensional parameters. So it scans only the Higgs mass and the cosmological constant appreciably, while the couplings do not change much. So it's possible to realize such a situation, but it's important to keep in mind that all these ideas that rely on the multiverse, including the one that I showed you with the two scalars, rely on the fact that you're changing from universe to universe. Typically, only the Higgs mass and the cosmological constant here, also the theta parameter. But if you start changing everything, the ideas don't work anymore. For example, in this model, if you were starting to change, say, the masses of phi plus and phi minus from universe to universe, then you would predict different values of the weak scale in different universes. All right, so after this, let's say, word of caution on these ideas, or at least, I mean, important feature to keep in mind, let's say, let me switch gears and tell you how to build a multiverse. And I'm going to start with an example by Brown and Teitelbaum. At the beginning of the 90s and of the 80s. You might feel like I'm going to introduce ingredients that are not really needed, because I could do the same with simple scalar fields, but I'm doing it as a nice introduction to Busso and Polchinski's idea that explains the cosmological constant in string theory plus a multiverse. So let me imagine that our theory contains a three-fold field. So a field with three indices that's antisymmetric in the exchange of any of its indices. This looks very much like the vector of potential in electromagnetism. So I can write a kinetic term for this object as a fourth form, which, if we want to be explicit, looks like this. So this will be my field strength, which I can put in the action. And this will constitute the kinetic term of my free form. Then, as usual, well, we're going to mostly talk about the cosmological constant. I want to add to the action also the Einstein-Hilbert part, plus some constant part. Then, so if I really want to obtain the correct equations of GR from this action, also, if my space-time has a boundary, I also have to add a boundary term, which I'm not going to really use in the following, but I'm going to tell you about for completeness. So this is the usual York, Hawking-Gibson boundary term, which might be important or not, depending on what space we're in. We're going to end up being also in spaces where it matters, but for us, it's never going to be important. So it's something that's useful to get the right equations of motion and write down everything consistently, but it's not going to change the classical equations of motions that we're going to write down. And the same is true for this four-form field. We have to add a boundary term also for that field, which looks like this. So I'm writing it down for completeness, as I said, in the cases of both boundary terms, but we're not really going to make any use of them in the following. So why did I write this down? Well, the reason why I wrote this down is that you can think of this F as an electric field in the same way as the two indices tensor in electromagnetism is the electric field when A is the vector potential. And if you write the equations of motion starting from this action, you're going to find something very similar to electromagnetism. So you're going to find this. And if you solve them, the only solution is that F is constant. and proportional to the fully antisymmetric tensor. The reason why this is true, so that A ends up being non-dynamical, is that this theory has a big gauge symmetry, which I can write in this way. You can check if you want as an exercise that that this is true. So if you add any two form and take a derivative and antisymmetrize the indices, or if you want in a more compact way, you would say A3 goes to A3 plus the theorem derivative of E2. Then you'll see that the Lagrangian doesn't change, and there are enough degrees of freedom in this transformation to essentially remove all the propagating degrees of freedom in the antisymmetric tensor. And so the most non-trivial thing that you can have is some background value for the electric field. That's it. If you plug in this solution of the equation of motion back into the action, you will find that you have a contribution for the cosmological constant from this background field. So you're going to find that your actual cosmological constant in this theory is whatever you started with minus the contribution from this higher form electric field. And so here we're starting to see where we're getting at, because just as an electric field can create electron-positron pairs and discharge, so the value of the background electric field decreases, in the same way we can couple branes to this free form, and these branes with opposite charges can be spontaneously nucleated, and when they are, they're going to change the value of the electric field, and in the same way, they're going to change the value of the cosmological constant. So we're going to have a process similar to Schwinger pair production, where instead of discharging the electric field, you're discharging the cosmological constant. So let's introduce these objects that couple to this four-form field. And I'm going to do it a bit heuristically, but it will make clear where the Lagrangian that I write down is coming from. So let's say I start with electromagnetism. So really a one-form vector potential and a two-form electric field. Then, well, we know how to couple charges to the electric field. We can write down the usual coupling to a current. And imagine that this current is generated by some particle that is moving along a word line, say an electron. And the coordinates along this word line are parameterized by the proper time of the particle tau. Then we know how to write the current. It's a standard exercise, so it's going to be localized around the position of the particle. And it's proportional to the forward velocity along the word line. So if we plug it back into the Lagrangian, we're going to get that we can integrate over the delta function, and we're left with a dt times the 0,0 component, now the determinant, times the charge the forward velocity and the vector potential. Here, in principle, we could go farther. Notice that this is really the proper time, because the metric along the word line, if you just take the determinant of the 0,0 component or minus the square root, it's just going to give you a boost factor. And then you can integrate in d tau trivially, eliminating the d tau in the forward velocity, and you're going to end up with the usual one-form integration along the word line of the particle. But we are not really interested in this expression. This one generalizes this in a simpler way. Because now, let's take an object with two indices. So let's say that we have a two-form potential. Then this is going to couple to a string. And the string is moving in the time direction, and it's spanning some word, some surface this time. And I'm going to need another coordinate that tells me where I am on the string. So before I had just the proper time parameterizing the word line of this particle, and now I have two coordinates parameterizing the word shape of this string. And if we just stare at this expression, it's not too hard to guess how it should generalize. So here we're integrating over the coordinate that's spanning the word line. Here we integrate over the two coordinates that span the word shape. So tau and sigma. Here we're coupling the vector potential to the forward velocity, and here we can couple it to the two kinds of derivatives that we can write down in terms of the coordinates of the string. Now, since I want to get to a fully antisymmetric object, I'm going to imagine that also my two-component object is antisymmetric. And so here I have only one possible contraction, the one where also the coordinates at the denominator have an antisymmetric symbol. The only part that I'm left to write is the charge. The difference is that now my E, even if I'm using the same symbol, is a charge per unit length, which makes sense because if I'm thinking of an infinite string, this is the only object that I can define. And then the total charge will be an integral of E over the coordinate sigma. And now you see immediately how to generalize to the case we're interested in. So we can add to the action that scans our cosmological constant something that looks like a charge, an integration over the three coordinates. Now we have three indices, so we're going to couple branes to this free-form field times our field and the three derivatives with respect to coordinates over the brane that we can write down. And here, well, E is going to be a charge per unit area. Again, this is not a proof, it's just an heuristic construction to show you where the terms in the Lagrangian that I'm going to use are coming from. The only, well, so it might seem like we've done our job, but well, there is one piece that is still missing. In the same way as I have the kinetic term for the free tree form, I would like the action for the free brane. So what happens to the brane if it's not interacting with our free-form field? And again, we can construct it pretty easily from starting with a single particle. So if you have a free particle, the action of a free particle looks like this, as you know from your classical mechanics courses, which we can write in a more easily generalizable ways. More easily generalizable way as dt times the determinant of the zero geometric along the word line. So again, this is just a usual 1 over boost. And so we see immediately that for our brane, we can generalize this to a tension, so a mass per unit area, now multiplied by the integration over my three coordinates times the determinant induced over the brane. Okay, again, this is not going to play a big role in what we're saying next, but for completeness, you should add to the Lagrangian also the free part of the action of the brane. And at this point, we have all the ingredients to see why at all I've done all this work to write down this model. Because as I was anticipating, we have charged objects under our, let's call it electric field. And so if the electric field is big enough, you can spontaneously nucleate branes and anti-branes. So you're going to make a bubble. And then the two walls having opposite charge will accelerate away from each other because they're still immersed into this background electric field. So it's in the same way, imagine having an electric field like this and popping out of the vacuum an electron and a positron. Then they would go away from each other, eventually getting as close as possible to the speed of light. And the same is happening here. So you can tunnel, let's say, to a new vacuum. So the process is really equivalent to semi-classical tunneling, where you have, instead of just the electric field, you have the electric field plus these two branes. And an electric field that has slightly decreased, of course, because you have to put enough energy to make the two branes. In practice, you can see it a bit more precisely, although I'm not going to give you the full derivation of the tunneling, but you can see a bit more what's happening if you write the new equations of motion after adding also the interaction with the brane. And the new equation of motion is similar to before, except for a few points in space. Let me write it down and then explain. Sorry, I should have said rho and sigma. Yeah, so you see, unless you are on the brane, the equation of motion is the same as before. So essentially, you have some object that is dividing space into two. On one side of this object, the equation of motion is equal to what it was before. And on the other side, it's also the same as it was before. So again, on the two sides of the object, you're going to have some constant effective electric field. But it's not going to be the same on the two sides, because the same equation predicts that from one side to the other is jumping by a factor of e. Yeah, so if you want the difference in C's between the two sides, it's precisely this charge per unit area that we were talking about. And so what's the story? So now we have all the ingredients. Of course, you have to believe me about the tunneling process, because to really do it in detail would require another couple of hours. But if you believe me, what's happening in this story? So we're imagining that we're starting with a big electric field that corrects the cosmological constant. And we are going to have some exponentially small but non-zero probability of nucleating a bubble, which is made of these branes. Okay, very roughly, you can think that half of the bubble is a brane of charge plus, and the other half is a brane of charge minus. And outside, you're going to have the initial value of the electric field, whatever it was, and inside, you're going to have a new value, which is smaller by a factor of 3. And then the walls of this bubble will accelerate away from each other under the action of the electric field, in the same way as I was describing for electrons that are swinging their pair produced. And as you can see, we're in a situation that's very similar to what we described at the end of the last lecture. So we start, let's imagine that we start with a large positive cosmological constant. Then the space-time here outside is expanding exponentially. Then you made a bubble that's expanding at the speed of light, but it will never catch up to all of the space-time outside, so long as the cosmological constant is positive. And so here you're creating a multiverse made of these nested bubbles. And the cosmological constant is decreasing as you go towards the center, let's say, of this multiverse. Okay, and it's decreasing by steps of order E. So at every step, the cosmological constant goes down by roughly E squared over T. So this is some practical way of populating a multiverse, or if you want, a toy model of the multiverse. The nice thing about this idea is that it also has a way of telling you why we might be in the universe with the smallest positive cosmological constant that exists. And again, I'm not going to do the calculation for you for lack of time, but I'm just going to tell you in words what might be happening. So we started with some large cosmological constant, and then we're jumping down in discrete steps. And at some point, we will be just above 0. Okay, so the next transition goes from positive cosmological constant to negative cosmological constant. And as I mentioned at the end of the last lecture, spaces with a negative cosmological constant have a finite radius of curvature. And also these bubbles have a critical size. If you make them too small, they never expand, they shrink back. And so if the critical size of the bubble to go from positive to negative is bigger than the typical size of the space that you're creating, you will never have this final transition. So it might be that this process stops exactly where we want it to stop. So at the smallest allowed positive cosmological constant. And what's the smallest allowed positive cosmological constant in this idea? Well, if you don't want accidental cancellations, it's going to be of order E squared. So that's the step of your scan, and that's the typical spacing between 0, the smallest positive cosmological constant that you can have in this multiverse X. And so you might be saying, fantastic, I solved the problem. So now I'm predicting that this quantity is whatever I observe the cosmological constant to be, and I'm done. And indeed, this is a very nice idea that was aiming precisely at doing this. The problem is that getting from here to here, you inflate it for an exponentially long time. So now, so now you're in this innermost universe where you inflate it for an exponentially long time, and the universe is completely empty. Let's say, fine, well, let's try to add some other scalar here that then rolls down its potential and reads it back. But of course, it's not possible because this tunneling process here, it will stop only if you're already at the minimum in some sense. Okay, so let's say that you had some scalar that was displaced from the minimum. From this mechanism, you have no way of tuning the cosmological constant at the minimum to 0. You're always tuning the cosmological constant to where you are at this point. So if you're saying at this point I am up here, then you're tuning this one, not this one. And so you might end up reheating the universe if you're in this situation, but again, you're not explaining why the cosmological constant is small, because if you're tuning it to 0 here it will be large and negative typically. So why did I bother to present this model if it doesn't work? Well, I bothered because it has all the ingredients, and probably it also, and actually almost certainly it was also the inspiration for the idea that actually works. And at the moment, many of us find the most convincing for explaining the cosmological constant. And this is Busso-Polchinski in 2000. Essentially, the story is exactly the same as what I've already told you. The only difference is that now imagine that you have many of these fields. Many of these 4 forms. This could be the case in string theory. For example, in M theory in 11 dimension, you have a 1-7 form that when you compactify to 4 dimensions gives you 2-4 forms. If you are inspired by string theory in this construction, you should also keep in mind that all charges are quantized. So in particular, what we call C would be quantized. I'm not going to tell you why unless you ask. That's because it doesn't make a huge difference for what you're going to say, but that's why in writing the contribution to the CC has some discrete numbers times the charges. All right, so now let's imagine that we are in this situation. What we just described was the case with j equal 1. And in the case where j equal 1, what you're saying is, well, my lambda 0 is some value. My discrete part of the cosmological constant spans some points on this line. So what does it take to have at least one point within an interval of order the observed CC from lambda 0? So you want these two terms to cancel each other and give you what we observe. Well, what it takes is that at least one of these points, let me change the symbol for clarity, falls within this interval. And so essentially, by this construction, you're predicting that your E square, as we've seen before, should be of the order of the observed cosmological constant. However, let me now imagine that I have 2 instead of 1. And here you will start to see why this idea is simple but powerful. So if I have 2, I'm going to be in some plane, and the discrete part in the cosmological constant here will live on a lattice in this plane. And now, well, I have some value for the initial cosmological constant, and I would like at least one point in the lattice to fall within a donut which has a width of order the observed cosmological constant. So wherever I am in this donut, the sum of these two terms is small. And so essentially what I'm asking is that the area of the smallest square that I can draw in this plane should be smaller than the area of this donut, which is just 2 pi times the radius times the width of the donut, which is and here, well, you don't yet see a big improvement. You see it a bit geometrically, but not really in the inequality. But now let me go to j arbitrary, bigger than 2. Then this inequality is going to become the following. So instead of 2 pi, now I'm putting the volume, the angular volume of a sphere. Now here you will have the radius to the j minus 1 times, again, the delta radius, so let's say the width of this multidimensional donut. And here you start to see what's going on. So essentially you have so many more dimensions that is much less of an accident to have at least one point in the lattice fall within the volume of this donut, because the volume of this donut is increasing a lot because of the angular dimensions that you're adding. And so in practice, if you ask, what does it take to get the cosmological constant that we observe if I start with some fundamental scale of order and Planck to the 4th? Well, it turns out that if you have about 100 of these guys, which they tell me it's not impossible in string theory, but I haven't checked myself, then you need these charges to be only of order, say, 10 to the minus 2 and Planck. So it's not so bad. Essentially, you're saying that if all the fundamental scales of your theory are close to M Planck, but you have enough of this object, you can still find a point in this multiverse where the cosmological constant is tiny, but your typical scales are big. So now nothing stops you from having this be phi dependent, let's say, and you're tuning this cosmological constant to be 0, and you're imagining that you're somewhere here, and then this guy rolls down the potential and reads the universe. And the difference between 0 and here that you have at your disposal now is of order 0.10 to the minus 2 and Planck. Before, the energy that you had at your disposal was just the observed cosmological constant. So here you can build a universe that works and looks like our own. Besides, you don't even need to do exactly what we were doing before with all the bubbles being one inside the other and scanning the CC hierarchically. Here, every time you make a bubble, you're just spanning a different value of n for one of these one forms. So typically, you'll make all these bubbles where the cosmological constant is always of order n Planck to the fourth. And then at some point, if you wait long enough, you will land in one lucky bubble where the cosmological constant happens to be accidentally small. And if you combine this with the argument by Weinberg that we discussed at the end of the last lecture, you have a possible explanation for the cosmological constant. So you have to believe that a multiverse similar to this one exists, and that we see such a small value of the cosmological constant because in the other universes, observers do not ever appear. You could ask if any of what I told you has anything to do with the Higgs mass. Well, the answer is that if you couple your fourth form to h squared, this multiverse also scans the Higgs mass. Let me just write it schematically. So this f squared is f mu rho sigma, f mu rho sigma as before. And you see immediately that as you change the value of the background electric field, now you're changing also the Higgs mass. Of course, nothing forces you to imagine that the multiverse is made out of these four forms. You can also imagine a simpler toy model built out of scalars. How much time do I have, by the way?
Well, say at most 15 more million.
15, okay, yeah, because I didn't check when we started.
Just a question. In this framework, how many bubbles you have to put one inside the other?
Yeah, that's a good question. So it depends on the details of the model. Let me tell you why. So I didn't want to write the scalar toy model, but actually the scalar toy model kind of precisely answers your question, so let me do it.
I would
Well,
say
actually, there's not even need for the toy model. Let me give you the answer. Okay, so here the cosmological constant is given by, well, okay, the toy model it's better, but it's given by a sum of different contributions, right, as we've written down. And so you can ask, what's the probability distribution of the cosmological constant in all these bubbles? And eventually, when you have many bubbles, just central limit theorem is going to tell you that it's a Gaussian, okay? So it's a Gaussian that looks like this. So this is the typical difference between potential energies when you go from one vacuum to the other. So in the model, let me just rewrite it. I don't know why I deleted it. I shouldn't have. So here, the typical difference in vacuum energy between one vacuum and the other is just E squared, right? Because if you move from one to the other, you're changing by a discrete value of E squared. Let me just say that all the E are comparable, okay? And then I have a single value of delta V, which is roughly E squared. And then the exponential of this Gaussian looks like this. It looks like, okay, my variable minus n times the typical value of the potential. Now, the typical value of the potential, we said that it's n Planck to the fourth, okay? Divided by n delta V squared. Okay, and this n is roughly how many things you're summing to get the CC. So it's say j plus 1. Okay, if you want, I can call it j. And so you see that if I really do the dumbest possible thing, so I really literally imagine that there is some constant piece which itself is of the same order of all the rest, and then I let this multivert scan it, then if you plot this Gaussian, it looks like this. It's a central value at n and Planck to the fourth. So n typical value of the potential. And it has a width which is delta V times square root of n. You see it from here. So typically square root of n times n Planck to the fourth. And so if you want to go to 0, like much smaller than Planck to the fourth, let me approximate the observed cosmological constant by 0, then you are on a very far away tail of the Gaussian. So essentially 0 has roughly a probability of order e to the minus n, sorry, this is squared, n v bar squared over delta v squared. So it's roughly e to the minus n. Okay, so you also have a 2 to the n times e to the minus n. So roughly, you need the number of bubbles that make this probability order 1. And okay, so to be fully precise, you also wanna add the dimensionful part, otherwise it doesn't make sense.
You have a question from Pascal.
Yeah, sure. Well, did you write it or?
No, Pascal, you can go on and.
Yeah, okay, thank you. Just a comment. What is your? I thought your delta V was of order e square, and now you write it of order m Planck in your expression.
Sure. I mean, I can put yes. I mean, I was. It's just that I didn't want to commit 100% the model with the 4 forks. So yes, if you do it literally in the model I just described, your delta V would be 10 to the minus 2 to the fourth and Planck to the fourth. So here you actually have a much bigger factor. So you have a 10 to the 8 times n in the exponential. Okay, but if you imagine that instead, say, the landscape that is scanning your cosmological constant is something simpler, let's say it's just a collection of scalars with some splitting between the minima of their potential. So imagine that you have now n scalars with 2 minima, and that your total potential is a sum from 1 to n of these n scalars. Then, if you're scanning your cosmological constant in this way, then your typical delta V is going to be of order n Planck if the energy density of the minima is, sorry, n Planck to the fourth, if your energy density of the minima is itself n Planck to the fourth. So this number of 10 to the minus 2 is kind of model dependent. Here I was trying to make a more general argument, but indeed it matters a lot, as you can see. So the details of the model matter for how many bubbles you actually make, because they enter in the exponent and they can enter as a big power. So, but thanks for asking. Yes. So what was I saying? Yes, that that you're in this tail of the Gaussian where the probability is very small. So if you want to ask how many macula do I need, you want to say that the probability of lambda integrated, say, between, I don't know, minus delta lambda observed and delta lambda observed around 0, you wanted to make it order 1. Okay. If you were centered in 0 instead of centered so far away, by doing this integral, you would just get the observed value times 2 to the n over delta v as to the order 1. And then you would find that 2 to the minus n should be delta lambda observed over delta v. And so this is 0.1 milli to the fourth over m Planck to the fourth. And if you take log 2 of this, you get order 100, well, a few hundred of the scalars and of these vacua, and you have to populate roughly the same amount of the same number of bubbles. If you are in the exponential tail, as well, thank you, Pascal, for the question, because it was perfect. Then you're gonna have here also this small exponential with an n and a number in front that is model dependent and could be big. So depending on the details of what's scanned in the cosmological constant, when you solve this equation, you might end up with, I don't know, thousands of bubbles or tens of thousands or a million, depending on what's the number in this exponential. But, so this is what happens in the dumbest possible landscape that you can write down. Because let's say you were going to write a supersymmetric landscape instead. Then in the supersymmetric landscape, you would be centered around 0. And then my estimate without the exponential would be the one that makes sense. And then you would find that you need typically 120 bubbles to see at least one with a small CC. And just to give you a feeling for what this means, if you want to explain the CMB, you need 60 e-folds of inflation. So as you were saying, I forgot if we were saying it last time or not, but you need 60 e-folds of inflation. So you need the exponential that tells you how fast the universe is expanding to become e to the 60. Okay, so if you check what this means in terms of how long you need the universe to inflate, you're gonna find not 120 because it's not the same exponential. Okay, you need to do a calculation that, if you want, we can do next time. But you will see that you need of order maybe 1,000 of these e-pods. So it's a factor of 10 more than just to explain the CMB. So it's not completely crazy numbers. They are in the ballpark of inflationary models that can work. Besides, I mean, the, let's say, initial idea for this multiverse was that you are in some de Sitter minimum, and then you just inflate forever until you tunnel away and you are not in de Sitter anymore. And then the last 6 e-folds are explained by a scalar that rolls down. But here we are moving into uncharted territory where I would need to give you an introduction also to inflation, and I certainly do not have time. So let me just, since I think we are at the end, right? Or do I, are we at the end?
Well, ideally, yes.
Okay, ideally, yes. Okay, so let me just make a comment then, which is that, well, some of these ideas now are being questioned by people that think that it's hard to build the de Sitter vacuum string theory, or maybe even impossible. And at the moment, these statements have some very plausible physical foundations, but they're at the level of conjectures. If they prove to be right, and maybe go even farther and show that even anti-de Sitter is in tension with explicit construction, maybe the final answer for the cosmological constant will be that just the consistency of the final theory of quantum gravity wants it to be 0. So some of these ideas have come to be questioned more recently, but I'm not going to enter the details of this debate during these lectures. The only statement that I'm going to make is that in these cases, at least at the toy level, you can build a model from the beginning to the end and see what happens. And you have good reasons to believe that it works. In the case of the conjectures, for the moment, they're just conjectures based on some examples in string theory and solid physics intuition. Having said this, I've gone much more slowly than I was expecting, but next time, which is our last lecture, I will try to do a few things for you. So first, I'm going to show you what happens if you have a landscape that is not a multiverse. So here we built multiverses, we talked about multiverses, but really the core of the idea, what's used to explain the cosmological constant at the Higgs mass, is that you have many realizations of the cosmological constant or the Higgs mass. So can we have many realizations of these parameters without a multiverse? Maybe if we can, it's even better, because in a multiverse, nothing guarantees that other parameters do not change from universe to universe. For example, in this construction with the 4 forms, if you really are inspired by string theory, you have absolutely no reason to believe that the other parameters don't change. Because as you compactify to 4 dimensions, you're not only going to have these 4 forms, but you're going to have a bunch of other moduli that when you change them and their vacuum expectation value changes, you're changing all the parameters in the standard model. And so maybe if you have a way to build a landscape, so a collection of many values for the CC and the X that is not a multiverse, you might have gained something. And so we will see next time how to do that and what you gain and what you lose by doing that. But we will try, although I have less time than I was hoping for left, also to go to the truly crazy stuff. So the more modern ideas that don't quite work, but might be hinting at some new explanations for the Higgs mass or even the cosmological constant. So I'm alluding to possible UV-IR mixing, so a possible behavior of our theory of fundamental interactions that doesn't look at all like the effective field theory intuition that we all have. Or maybe also I'm talking about some more subtle symmetries that are in this category that is being developed by Seiberg and collaborators of generalized or non-invertible symmetries that might have something to say about the Higgs mass. As I anticipated, these ideas don't quite work, so they're not really a model that you can write step by step and show that does its job, but I think they're very interesting inspirations for what might be actually happening. And then, well, maybe we will also try to give some biased conclusion comparing all these ideas that we've seen in these few hours together. Okay, thanks, and sorry for this.